Hello again. Thank you all for being here. We will now continue the activities of the Amazonia Symposium as now with our opening seminar, opening lecture, and it's my honor and pleasure to present to you Professor Carlos Herdeiro from University of Aveiro. For those who do not know, Professor Carlos Herdeiro is also a permanent member, permanent docent of the graduate program in physics of Federal University of Pará. Also, I mean, not only contributing with research, ongoing research and collaborations, ongoing with projects, leading projects, and participating in many projects of the program, but also giving sometimes courses and presently and in the past and in the present moment supervising students, master students and PhD students. So uh, I don't know how to say exactly the expression in English. Professor Carlos Herdeiro is a prata da casa, right? He said silverware, home silverware, something like that, right? So it's not necessary to keep long talking about him because almost everybody, if not everybody, really knows already Professor Carlos Herdeiro, not only for the excellence of his research, but also for the excellence of his talks. This gives you a responsibility that it's not too much to carry because you always do it very, very well. But more than that, I should say that he's a good friend. And perhaps, at least obviously from the personal point of view, the highest quality of Professor Carlos Herdeiro, for whom I ask you a round of applause.
So after these kind words, I can only disappoint you, but I'm used to that. Thank you very much to my good friend Professor Crispino and the remaining organizers for setting this meeting. I'm in the organizing committee, but I did very little, as you can imagine. It's a great pleasure to be once again here in Belém and meet so many friends, collaborators. So today I've decided, is it possible to actually remove this thing from the bottom here? Is there anything I can do or someone can do? Do you know? Well, anyway, so I'll just keep going, and if there's something that would be nice. But if it isn't, it's possible. That's okay. So my title today is same as ever, looking for invariants in the black holes landscape. And this is essentially based on a talk I've given in Copenhagen in this conference, Black Holes Inside Out, that was in August this year. And there was a write-up, and well, I wrote something and kind of gives a spin to the science that is presented there. For the group members here, I must say that I've given essentially the bulk of this talk here in August, so I hope you won't get too bored. But anyway, let me start with the following thought. In science, one is constantly looking for the next breakthrough, the next game changer, and it then becomes easy to overlook the basic, which is what is the same as ever. And well, this came to my mind because I was reading this book by Morgan Housel, same as ever, which I thought had some interesting essays, not about science. And at some point, well, actually, in the beginning, he starts with this quote from Jeff Bezos, who is said to make the following remark, and that's the following. I very frequently get the question, this is Bezos speaking, what's going to change in the next 10 years? And that is a very interesting question. It's a very common one. I almost never get the question, what's not going to change in the next 10 years? And I submit to you that the second question is actually the more important of the two, because you can build a business strategy around the things that are stable in time. So, what kind of question looks for the same as ever in our scientific field? Well, one possibility is this kind of question. So, what is general for equilibrium single black holes and what's model dependent? There are paradigmatic features, black hole features, that we've learned in our first courses on black holes from the canonical electrovacuum general relativity solutions, which are, of course, the ones within the Kerr-Newman family. So, for instance, black holes are a spherical horizon topology, or spinning black holes have an ergo region, or black holes have light rings and other bound photon orbits, or black holes have no hair. And many of these and other features have phenomenological impact. So it's quite natural to question the generality of such features in broader classes of models. And what I would like to do with you today is to focus on these two aspects here, the light rings and the hair, although these two are very interesting and also have other kind of surprises. So I will try in this talk to have a kind of a balance between generality, which is always desirable, and concreteness, which is often enlightening, even if exceptional examples are quite often just academic, but they tell us how things can be different. So I'll start with some general statements about light rings and then also about hair before moving to a selected family of examples and then some final comments and outlook. And as a comment, I would like to say that in this talk, I'll mainly focus on models without gauge invariant fields. Because introducing these fields actually leads to many possibilities for non-Kerr-Newman black holes, and I cannot review them all here. So let me start with some generic statements. And these generic statements often start with good questions. And the answers often involve assumptions. And they inform us of how we can circumvent these statements by, of course, circumventing some of these assumptions. So here's the first natural question. Do all black holes have light rings? And these are planar, in some appropriate sense, bound photon orbits. So light rings are extreme examples of light bending, as you know, and their existence and properties have relevance for black holes imaging and ring down. So there is a generic statement, which by now it's well known, certainly for this audience, I think, which is the following: that a stationary axisymmetric asymptotically flat black hole in d equals 4 dimensions with a non-extremal topologically spherical killing horizon admits at least one standard light ring outside the horizon for each rotation sense. This theorem does not depend on field equations. And I would like to emphasize, moreover, that it does not even assume that the black hole has a Z to north-south symmetry and hence an equatorial plane. In this respect, actually, it's interesting to mention that there are, in fact, a few examples of black holes, even with a connected event horizon. If you go to non-connected, there are many examples, which do not have a Z2 symmetry and still possess light rings as predicted by the theorem. So here's a kind of acute example. This is a black hole solution in Einstein-Maxwell-Dilaton theory. It's a rotating, electrically charged, magnetically charged black hole. So it's an academic interest, but the black hole doesn't have a Z2 symmetry. So this is the isometric embedding of the horizon, and you can clearly see it's not Z2 symmetric. North and south are different. But actually, it does have the light rings as predicted by the theorem. And moreover, this black area that you see here, often called the shadow, is Z2 symmetric, although the lensing is not. And there's an interesting story here, which I will not tell you more about. I don't know if Pedro will talk more about non-Z2 symmetric solutions. Maybe yes, maybe not. It's a long time still to your talk. You'll have time to decide. So this light ring theorem exemplifies a field equations independent statement. So it's therefore valid in generic metric theories of gravity. It is topological and associates to light rings this topological charge, which was introduced earlier in this paper here. The central idea is that light rings are critical points of appropriately defined two-dimensional potentials. So here's an illustration of such a potential for Schwarzschild. So there is a potential in the non-killing directions, here the radial and the theta direction, and as you can see, there is a critical point over there. These potentials can be used to define on this two-dimensional space vector fields as their gradient. And calculating a closed contour, or assuming any closed contour around in this two-dimensional space and circulating that vector field, the winding of the vector field defines an integer topological charge by this simple formula. It must be a multiple of 2 pi, of course, and this integer number here is called the topological charge. So this is the angle that the vector field will do with some reference direction, which is arbitrary. So to exemplify this, you can consider the simplistic example. Again, Schwarzschild, here's one of these vector fields. As you well know, here in this case, the light ring sits at r equals 3m and theta equals pi over 2. Of course, this is just a choice of coordinates. There's a kind of a photon sphere. And then you choose any contour. It doesn't need to be smooth, just needs to circle this light ring. And now you look as you go around the contour in any given direction, say counterclockwise, you look at how is the winding of this vector field. So for instance, you start here and you go counterclockwise and you see that the arrow is actually circulating in the clockwise direction once. Because the winding opposes the circulation, the topological charge is -1. If you try with any other contour enclosing the light ring, you get the same. It's topological in that sense. If you do a contour that does not enclose the light ring, then you do not get winding. The winding is 0. Topological charge is 0. But not all possible light rings with, for an arbitrary geometry that you can come up with, have this topological charge -1, meaning that the winding opposes the circulation. So standard light rings, by which I mean Kerr-like, the ones like in Kerr, Schwarzschild, obviously, they do have this property. And this is associated to the fact that they are saddle points of the potential. But you can have what we call exotic light rings, which are Kerr-unlike, which would be either minima or maxima of these 2D potentials, and they turn out to have a topological charge of +1. Moreover, the topological charge is additive. That's a simple, kind of important property, which means that if you have a contour that encloses more than one light ring, then the total topological charge is just the sum of the individual topological charges. Then, to establish the theorem, we look at the contour, or a contour C, that, in the limit, encloses the whole of the spacetime outside of the horizon of a black hole. You assume there is a black hole. And to assume there is a black hole is essentially a boundary condition. Of course, you have to assume the black hole, say, is asymptotically flat, and that is another boundary condition. So at the end, it's an issue of boundary conditions. So if you assume that there is a black hole, under the conditions of the theorem, in particular, it's a killing horizon and it's a non-extremal. It's asymptotically flat. It must be regular. So there's an axis, there's regularity conditions. And then you take the limit of the contour as to enclose the whole of the space-time outside of the horizon. You can see, just using the boundary conditions, that the topological charge is -1. So this works for both H plus minus potentials, and this means for each rotation sense. This does not exclude, however, that black holes can have more than one light ring for each of the potentials, but the extra ones, if they exist, they must come in pairs and with opposite topological charges such as to keep the total topological double. So I emphasize no field equations were ever used to obtain the result. Perhaps you would say that's to be expected. Black holes should have light rings. They bend light a lot. But you'd be wrong. Because there are, in fact, examples of black holes without light rings. And actually, the theorem offers you a sort of a guideline of how to find them. So let me illustrate this. The asymptotically flat Schwarzschild black hole has omega equals -1, as we've seen. If we could immerse it in a background where the background itself would bring a light ring with topological charge +1, then the total topological charge would be 0. There's a sort of nonlinear superposition. Well, but what kind of exotic background would that be? Well, it turns out that there's something well known to relativists, which is the Melvin universe of electrovacuum, a sort of constant magnetic field that is self-gravitating, or a uniform magnetic field. And it has the property that bends light so much in the outskirts of this universe that it actually produces a light ring, which is stable and has topological charge +1. So then, if you actually put a Schwarzschild black hole in such a Melvin universe, the total topological charge is 0. And this does not mean there are no light rings, but for sufficiently large magnetic field parameter as compared to the mass, indeed, there are no light rings outside of the horizon. And since light rings are these critical points in the light scattering problem, you would expect a dramatic impact in the imaging of one such beast. And that is actually true, although it's an academic example. So if you set up your observer looking at the black hole, and you are in one of these situations where the magnetic field is large enough such that you do not have light rings, there's a celestial sphere emitting light, and to make things fun and colorful, you decide to color your celestial sphere with these colors, so that light comes with different colors. What you see as the observer is that if you send light rings straight at the black hole, oh, they fall at the black hole, but the absence of the light rings translating that if you send light rays along the equator in any given direction, the black hole is over there, they will end up falling into the black hole, except actually in the opposite radial direction. This gives this panoramic shadow, which is a dramatic kind of impact of this absence of light rings. And it illustrates, that the light rings do have an impact on this sort of imaging properties of black holes. So in fact, the analysis of light rings and their non-planar generalizations, which are called fundamental photon orbits, or some people call them, we do, they provide a simple, albeit not a precision, diagnosis of how non-kerr the phenomenology of some alternative model is. So it's kind of a simple diagnosis. Of course, if you'd like to do more precision things, you have to work harder. And looking at this topological charge with different boundary conditions has proved to be a sort of informative technique. I've listed here an incomplete list of examples inspired by this topological charge technique. So I'll highlight a few of them. So this topological charge is -1 for black holes. Also in other asymptotics like ADS and DS, there are some assumptions. It's not completely general here. This swirling universe, and also for some horizonless objects like traversable wormholes. But for topologically trivial, asymptotically flat, smooth, horizonless compact objects and families of echoes, exotic compact objects, or UCOs, ultra compact compact objects, the topological charge turns out to be 0. Then there's some families of solutions like Einstein-Maxwell dilaton with a varying coupling, where actually the topological charge can vary in a non-continuous way, in a discontinuous way along the family. So for instance, in these Melvin backgrounds that you always have for this Einstein-Maxwell dilaton, So for the dilatonic coupling closer to the Einstein-Maxwell value, you have this omega equal to zero, topological charge is zero, as we've seen. But at the Kaluza-Klein value, it changes discontinuously to omega equals minus one. And that's what you have for values of the coupling above the Kaluza-Klein value. There's also connections with the ergo region, the existence of an ergo region, and the existence of light rings. There's generalizations to higher dimensions and the non-spherical horizons, multi-black holes. Here it's essentially additive. There's generalizations where photons, to models where photons do not propagate along null geodesics of the space-time metric, like models of nonlinear electrodynamics. And the technique has inspired other things, like some sort of similar technique for some special time-like circular orbits or something related to black hole thermodynamics. So it's been a rewarding technique. And sometimes you look at an old subject in a different way, and all of a sudden new opportunities arise. I think that's a little bit of the lesson. I would like now to move on to the second question that I promised to address. And I would phrase the question as follows: do all asymptotically flat black holes have no hair? So, this is an old question as well. And by this one could mean that are all black holes uniquely determined by their mass, angular momentum, gauge charges, all of them being asymptotically measured quantities subject to a Gauss law and no other independent characteristics, to which hair provides a sort of general umbrella or a metaphor if you'd prefer. So here are the two types of generic statements, theorems, that one could address this question with. So, firstly, in electrovacuum, there's a set of uniqueness, well-known theorems that have defined the field of black hole, classical theory of black holes since the 1970s, establishing that asymptotically flat stationary black hole solutions with a connected event horizon fall into the Kerr-Newman family. Mathematicians will tell you there are some assumptions here, but this is sort of well established. Secondly, there are no hair, which you can think of as no-go theorems, which are beyond electrovacuum. There are many such type of theorems or arguments applying to different classes of models under different assumptions. So here's a partial list. It's taken from a review from a few years ago. I wrote with Eugene Radu for models where scalar fields, for models of scalar fields, no gauge fields, um, and where the scalar field is not subject to a Gauss law. Yeah, this cutting is not nice, but that's it. Um, so let me tell you, for the ones of you that might not be familiar, because the word theorem might sometimes, kind of frighten people, scare people, but there are some very simple arguments that may be quite powerful. And a simple and paradigmatic example of a no-hair theorem is this one due to Bekenstein that uses only the scalar field equation, not the Einstein equations. And it's really simple. You consider a stationary axisymmetric asymptotically flat black hole spacetime. You write the metric in coordinates adapted to those symmetries. So Tr, the non-killing, the r theta non-killing coordinates, T phi the killing coordinates, so that the killing vectors are like this. The first assumption is that the scalar field is canonical, which means the kinetic term is canonical. So there are many models where you have non-canonical kinetic terms like quintessence, these kinds of things. And it's minimally coupled to Einstein's gravity. Of course, there are many models where it doesn't happen, scalar tensor theories in the Jordan frame. And you allow the possibility of a potential. So something simple but fairly generic. Then the scalar field obeys this possibly nonlinear Klein-Gordon equation here. There's a zero over there. Nonlinearities will come from the derivative of the potential there. Then, as a second assumption, the scalar field is supposed to inherit the space-time symmetries. So if we've chosen the coordinates above, that means that the scalar field should be invariant when dragged along the t integral lines, and the same for the phi integral line. So it's independent of t and phi. This seems quite innocuous, but it's actually not. Opens a lot of possibilities if you do something where this is not true. So then what you do is you just multiply the Klein-Gordon equation by this phi. You integrate over black hole exterior space-time. So and you get that. After integrating by parts, you get a bulk term and this boundary term. You actually get two boundary terms, one at infinity, but if you assume the right fall off of the scalar field, that vanishes. And one at the horizon also vanishes, simply because it's a killing horizon. So the normal is a combination of the killing vector fields. And so because we assume that this is independent of the killing directions, then this must vanish. Now, to extract the conclusion, we must say something about the potential, otherwise you cannot say anything. Um, and in the original paper, Bekenstein took a condition that was a bit weird, honestly. It just said that phi times the derivative of phi with respect to the vector field, to the scalar field, sorry, is non-negative. This applies, for instance, if you have just a mass term, but it doesn't seem to be very well motivated. I'll come back to that. Um, so since the gradient of the field is orthogonal to both Keeling vectors, and then it must be space-like or zero, so the first term in the integrand is going to be non-positive, so because of this minus sign. And the same happens to this one here because of that assumption. So they have the same sign. So they have to be zero because you cannot integrate something that is non-zero, has always the same sign, and end up with zero. Again, remarkably, this did not use the Einstein equations. It's a very simple, very powerful argument, but didn't use anything about the Einstein equations. The same theorem was actually sketched in the same year in a paper by Hawking, famous paper, on the absence of new black holes in Browns-Dickey theory. And yeah, there's an interesting story because these two papers appeared in the same year with the same argument, but because essentially what Hawking did was he went to the Einstein frame and did the same argument. But they don't cite each other, so there seems to be a common origin of this argument. And well, there's a story there. Anyway, um, okay. So as a remark on that assumption number 3, it does not seem particularly significant, as I've said, and it may be violated for potentials of interest. So over the years, different energy conditions have been assumed in different arguments that have been given in the literature for this class of models, still in this class of models. So for instance, instead of using that sort of condition for the potential, you could say that the potential has a second derivative, which is non-negative, this convexity condition. Or you could use, and this uses a sort of variation of the Bekenstein argument, where instead of multiplying that equation by phi, you multiply by the potential. Using a different sort of argument, which is a virial argument, you can impose positivity of the potential, and you get some result as well, some obstruction. Or you can use the weak energy condition. But the common point here is that all of them apply if you have just the potential to be a master. All of these different arguments would rule out black holes with scalar hair, non-trivial configurations around the horizon if the potential is just that. Things actually turn out to unexpectedly change, though, if instead of the real scalar, you have a complex one. In fact, all of these theorems give us hints, which sometimes are confirmed, sometimes are not, how to get hairy black holes with a sort of non-trivial scalar configuration, in this case, around them. So this is the same table as before, but now I've added here the third column, where there are examples of known scalar hairy black holes with a regular geometry outside and on the horizon. So even though violating one of these three conditions that I've set, one, two, and three, does not guarantee by itself the existence of such hairy black holes, in some cases you can. Um, and for instance, this case, in the case of violating a non-minimal, so the minimal coupling assumption, there's a very well-known solution, an early example, which is this BBMD black hole that appears when there's a scalar field with conformal coupling. Violating the energy conditions, it's fairly easy. Then you can, I mean, anything goes, and you can engineer things even. But these things are typically unstable. There's a non-canonical kinetic terms like in Einstein's Kerm. This is also an early example. There's very interesting examples in other more complicated scalar tensor theories, and there's been a lot of work in black hole scalarization, which falls into that class. But the example that we've been focusing on is something that violates the more innocuous appearing condition number two, the symmetry inheritance. And this is the family that I'll focus on this talk, and I would like to share to you some new results, some old results, but also some new results about this family of models. So insight is often gained by looking at concrete examples. We want to make general statements. We want to, know the invariants in the black hole landscape. But often, if you are lucky enough to find them, is because you are looking at special examples, and then perhaps you find some pattern that generalizes. If you look at concrete models, you should have some guidelines, because then there's too many possibilities, and so you should resolve what's reasonable and what's not. So here's a possible list of theoretical reasonability criteria for any non-Kerr compact object. Of course, it depends on your purpose, but if you want to consider these certainly as candidates for realization in nature. Now, some theoretical criteria could be the following to appear in a well-motivated and consistent physical effective field theory. For Kerr, of course, this is GR. It's an incomplete theory, but within its regime of validity, it's something that it seems to be self-consistent, although it's not complete. It's not UV complete, and it has singularity, and so on and so forth. Second, we have this need to form the things that we would like them to exist. That is, if they exist, there should be a dynamical formation mechanism, which for Kerr, it's gravitational collapse. There could be accretion, there could be mergers to change the black hole properties. And then it should be sufficiently stable. And here the keyword is sufficient, because absolute stability is not mandatory for physical relevance. And for Kerr, mode stability has been established long ago. The linear and nonlinear stability in a mathematical sense, proof of stability, is an ongoing effort in the mathematical relativity community. There's a lot of works, but for physicists, many of them are quite satisfied that this is a good model and dynamically stable. And these two conditions are what I call dynamical robustness. It's something that we know could form, and this could be living for sufficiently long time to play a role in whatever process you would like it to play. Of course, then if you'd like it to describe or to consider it as a candidate for the data that we have, there's something else. Then you have to derive the correct phenomenology, electromagnetic and gravitational wave channel, compare it with data, and then assess the validity of that comparison. And at the moment, I think it's fair to say that there's no clear tension between observations and the Kerr model. But yet, some precision phenomenology of reasonable non-Kerr model is quite desirable, because differences can hide in small details, and you might get a clearer idea of those details you should look at by seeing in alternative models what are the details that change, especially in reasonable models. So I shall briefly consider one family and the related mechanism of potentially reasonable, and I emphasize the word potentially reasonable non-Kerr models of black holes, in this case with bosonic hair. So this family, and this is the simplest example that has been known now for over 10 years, now. Note that this is looking precisely like the model that I was enunciating those theorems and saying, oh, there's all these theorems that apply and they rule out, hair for this type of model. But there is a key difference here is that the field is complex. And this allows us to violate assumption 2 of Bekenstein's theorem, the symmetry non-inheritance, it's called. And it's exactly when that happens that you have the symmetry non-inheritance. There's a discussion of this in this paper by Smolich, if you'd like, that this thing happens. And this is actually quite common in models with, say, non-abelian gauge fields. People have put forward ansatz where you have that the space-time symmetries are very different from, the symmetries under which the field can be invariant. But if you do that, there are indeed black holes within general relativity, not alternative theories of gravity, although this is again generalizable here, with matter obeying the main energy conditions, which can yield distinct phenomenology, and they are asymptotically flat, regular on and outside the horizon, continuously connected to the Kerr solution, continuously connected to relativistic Bose-Einstein condensates, which are called boson stars, with an independent scalar charge, which we call primary hair because of that. Um, so, moreover, as I'll argue, they can form dynamically and be sufficiently long-lived, at least in some regions of the parameter space. Before giving you more details, let me make 2 comments. One, the solutions are numerical. So I kind of anticipated you wouldn't be able to see that, so I said. So the solutions are numerical, but mathematicians have been kind enough, you don't see it because it's hidden over there, mathematicians have been kind enough to give an existence proof. And that was done by Kodosh and a collaborator in 2017, and it's published in Communications of Mathematical Physics. And the second thing is that there's a new scale here, which is this mass parameter, which you can think of as the Compton, as a length, as the Compton wavelength associated. And these can single out black holes of a certain size to become hairy. And the ultralight range is particularly interesting for astrophysical black holes because it makes contact with things as superradiance. And this is a very interesting connection. So without entering too many details, these solutions are typically found with this type of ansatz here that you see adapted to describe spinning black holes with the horizon at this r equals rh, this parameter that you see there, and an angular velocity omega h that omega h that will be the value of this function here at the horizon, which is r equals rh. So the scalar field has this phase with a frequency w here and this integer azimuthal harmonic index m. The fundamental family of solutions as m equals 1, but there is a sequence, a countable infinite sequence of solutions for different m. And there's, as you can see, a phase angular velocity, which is precisely the frequency over m. And solutions exist under the synchronization condition called, which is that the angular velocity of the horizon equals the phase angular velocity of the field. So that's why it's called the synchronization condition. So there are 2 rotations which are synchronous. So the intuitive idea for this family of solutions is that there is a continuum of hairy black holes interpolating between Kerr and these rotating boson stars. The latter are solutions in the same model that have been known since the 1990s and are typically described as mass tori in general relativity because the morphology of the energy distribution is toroidal. Topologically, they are trivial, but the morphology is toroidal. Thinking about them as this sort of nonlinear superposition suggests that we should look at 2 limiting cases. So near the Kerr limit, the scalar field is small, and we can use a test field approximation. On the other hand, near the black hole, the boson star limit, The black hole is small, and we can use a test particle approximation. So both these cases, interestingly, can lead to insights on the solutions and on their dynamics. So let us look first at the Kerr limit, where we consider a test scalar field and ask, how the hell is it possible that a scalar field could be in equilibrium with a horizon? Because if you are bored with my talk, you can do the following. Write down the Schwarzschild metric and put the Klein-Gordon equation on top of it. Look for a spherically symmetric solution, and you will see it diverges on the horizon. It's a one-line computation, logarithmic. And therefore, if you try to do the energy momentum tensor, you will find out that it blows up and the test field approximation is not valid anymore. So why can you, in some circumstances, have this scalar field minimally coupled in equilibrium with the horizon? Well, sync actually means that you are at the threshold of superradiance and there's zero flux through the horizon. And to detail this, you can also do a simple analysis, a linear analysis. So you consider the Klein-Gordon equation on Kerr as a test field. You perform the standard mode decomposition that you've seen many times in terms of spheroidal harmonics. And this leads to the Tucholsky equation, which is actually obtained independently by, so this is the scalar version of the Tucholsky equation. It was also obtained by these people here. And imposing the bound state condition, because you have a mass term in this case at infinity and appropriately chosen ingoing boundary conditions on the horizon, one obtains generically quasi-bound states. Not bound states, which would have a real frequency, but quasi-bound states that have a complex frequency. In terms of a quantum mechanical problem, is that it's because the Hamiltonian is non-Hermitian. And that's because there is flow of energy, or there's the potential of flow of energy through the horizon. Now, the frequency is complex, and the sign of the imaginary part depends on the relation between the real part and that critical frequency that you see there, which is precisely given by the sync condition. So, if the real part is greater than the critical one, the imaginary part is negative and the mode decays. So, this is the only regime that you see in Schwarzschild. If the real part of the frequency is smaller than the critical frequency, the imaginary part is positive and the mode grows. So this is the superradiant regime that President Tucholsky called the black hole bomb. And finally, if the real part of the frequency is exactly equal to the critical frequency, the imaginary part vanishes. And the modes are true bound states in equilibrium with the Kerr black hole. So the hairy black holes can therefore be regarded as a sort of nonlinear continuation of these linear bound states that you can understand as a quantum mechanical problem. So you may question, but this seems highly fine-tuned and therefore unstable. But you may be aware that dynamical synchronization occurs in many physical and biological systems. Communities of fireflies and crickets, sets of metronomes and pendulum are amongst the examples where the individual cycles converge to the same phase if appropriate couplings are present. So here you can see an experiment in the mangrove forests of Thailand where thousands of live fireflies are made to synchronize their flashes by a few computer-controlled LEDs. If you are unaware about this dynamical synchronization, looking at that system, or for instance, a set of pendulums in phase, you may think this is a fine-tuned configuration. With noise, this is better, but let me see. Okay. However, this is not really the case. You can start with arbitrary initial conditions, and the synchronized configuration is a dynamical attractor. So here the right coupling is simply to provide a moving base. After enough time, you can see that the synchronized configuration is achieved. This is actually a very simple physics experiment that you can repeat, and you wouldn't imagine it has anything to do with black holes. There you go. So in Newtonian gravity, this dynamical synchronization occurs in closed binary systems. And what's well known, and you see it every day if you look at the moon, is that tidal interactions tend to synchronize orbital and rotational periods, locking them. So in the Earth-Moon system, the latter has actually reached an equilibrium stage. And that's why the moon is showing always the same face towards the Earth, giving rise to the expression dark side of the moon, which is not dark at all. Um, and this can be seen here from this animation. The other thing hasn't happened yet, because of course the Earth is bigger in the system, and but it's tending towards, and that's why there is this flow. The moon is drifting away from us, and days are becoming a bit longer. So it's the Earth kind of getting closer to that synchronized configuration. This is common to moons in the solar system. There's actually one planet, which is the Pluto-Charon system. It's almost a binary planet because the mass ratio is much closer than one, and it's fully synchronized. The three frequencies in this case. So in our case, the sync state, which is the hairy black hole, could be obtained by superradiance. And evidence comes from these fully nonlinear simulations that were done successfully a few years ago in a cousin model, which is the Proca model, not the scalar model. This is because of an issue related to the time scales. So the superradiant instability in this model is faster. So what happens is that if you allow in this cousin Proca model, where you have a complex, massive, of course, Proca field, minimally coupled to Einstein's gravity, and you have a rotating black hole, part of the energy of this rotating black hole is going into this cloud that grows. These are different values of the coupling, which is essentially defined by the mass of the black hole and this mass of the scalar field. So it grows the energy that is in the cloud, and then it saturates. So this is for the mass in the cloud. This is for the angular momentum in the cloud. And what you see here is the spin down of the black hole. The black hole spins down, and what you see when it saturates is this synchronization, where the angular velocity of the black hole is meeting the phase angular frequency of the dominant superradiant mode. So this is a kind of a guise of synchronization. And the black holes that are achieved in this way, you don't see it because it's hidden there. They could be identified as black holes with this synchronized Proca hair a few years ago after the paper by East and Pretorius was out. But you cannot extract arbitrary amounts of energy in this process. Actually, in the simulations, the most they could see is about 9%. And there's a kind of theoretical bound from a thermodynamical argument known from Hawking many years ago, 29%. And if the process is more or less conservative, as the simulations seem to show, there's very little dissipation into radiation, gravitational radiation in the process, then we could give an argument that we would expect the energy extraction bound to be for about 10% in both the vector and also the scalar model. So for the scalar case, similar evolutions could not be done, but I would like to report some preliminary results, and Jordan will then develop on this that have been used, not for evolving the superradiant instability on Kerr of a scalar field, but evolutions of black holes with synchronized scalar air via fully nonlinear evolutions. So here I want to show you briefly two examples. This one is a fairly hairy black hole with 25% of the total energy in the hair. But the gravitational center in this case is still the horizon region. Okay, so the gravitational pull is still being dominated by the black hole region itself rather than the cloud. For the timescales that we have explored so far, you do not see any relevant dynamics. So on the left, you see here the scalar energy density from above, which is toroidal, and on the right, you are seeing the real part of the scalar field. So the phase dynamics, just phase dynamics. So there's a very small horizon compared to over there. There's a very small horizon compared with the scale here of the energy distribution of the scalar field outside. Um, and during the evolution that was pushed, if you'd like to know, I guess, I don't know if Jordan has an update, but about 3,000 in mass units, nothing special occurs. So they are dynamically robust, at least for these time scales. Nothing catastrophically is occurring. You don't put it there and immediately it is destroyed. In fact, in longer time scales, you do expect something to occur because these hairy black holes are themselves unstable against superradiance because they have an ergo region. And this has long been suggested in the early days of these solutions that this could lead to them being afflicted by superradiant modes with higher M. And this was confirmed in this very nice paper by Ganchev and Santos a few years back. However, these higher M modes have also longer timescales. So as an example, we could consider very massive, really supermassive black hole with 10 to the 10 solar masses, and we know of such black holes in the universe, and a scalar field with a Compton wavelength comparable, which would give us this kind of scale over here. Then, whereas the timescale for the leading mode to form a hairy black hole, the fundamental solution with m equals 1, is an astrophysical timescale of the order of 10 million years. The timescale estimated for the hairy black hole to become unstable and develop this m equals 2 mode, which is the next one, is about 10 billion years, 1,000 times larger, which is about the age of the universe. So to the question, is the hairy black hole the end of the superradiant instability of Kerr? The answer is, in theory, no. They are still afflicted by superradiant instabilities of higher M modes. And the precise dynamics is still to be understood. But in practice, it can give rise to this notion of effective stability, although this is much more interesting for supermassive black holes. So let me now show you some new results looking at the boson star limit, where we consider a point part approximation for the black hole, which is inside the environment of this very massive boson star as compared to the black hole, and ask, is there equilibrium between a small black hole and a big boson star? Is this equilibrium stable? There is an equilibrium, simply by symmetry, but is it stable? Well, the first thing to consider, and some of you, of course, know this, is that the spinning scalar boson stars themselves, they develop a non-axisymmetric instability at moderately long time scales of the order of 1,000 times, 1,000 light crossing times. So you can see here a visualization that I've shown in many talks of a fully nonlinear evolution of the Einstein-Klein-Gordon system. That's here on the left panel. The color code denotes here the scalar field amplitude. And when this non-axisymmetric instability kicks in, an apparent horizon forms, as you can see here on the right panel. So there's a mass here of the apparent horizon. The energy in the scalar field goes down. Being swollen by the black hole, signaling that there's black hole formation. So these stars collapse into a black hole. So you could imagine, well, but it could be that the presence of a small black hole could mitigate this instability, perhaps, wishful thinking. In fact, it was wishful thinking. It turns out that the black hole and the boson star form an unstable equilibrium. And moreover, this is sort of obvious and can be understood in a geodesic approximation on the background of these boson stars, hence the point particle approximation for the black holes, or if you are lazy, I am a bit sometimes, even in a Newtonian toy model. And so you can do the following. So you consider a thin ring This is now Newtonian physics. Radius r, and this is in a cylindrical chart. You take the ring, say, on the equatorial plane. It's centered at the origin. Its gravitational potential, it's a constant mass density. Its gravitational potential, you can very easily compute, is given by this. So there is a mass density that's going to be irrelevant, but it's constant along the ring. Um, then along an equatorial radius, you can see how this potential is, and this is the potential. Well, you can immediately see that the origin is an equilibrium point, but it's an unstable one for radial displacements, not along z, but for radial displacements, it's unstable. Under small perturbations, a particle at the origin is falling towards the ring, and that's not a big surprise. So you see here, well, you don't see here, but you would see here, if this would allow, an inverted harmonic potential if you do the expansion of that potential close to the origin. So that's it. And this seems to be exactly what we see in the nonlinear evolutions that Jordan is doing for very hairy configurations where the gravitational center is the scalar environment. So the very, very hairy black holes. So in this example, the hair is almost 90% of the total space-time energy. And so from the beginning of the simulation, the black hole starts moving. Although these are coordinate-dependent statements, the motion seems to spiral up. And that's kind of to be expected. So in the Newtonian example, if you give a little kick, it would just go radially. But now you have dragging because it's a spinning spacetime. So it kind of just spirals out. And as it gets to the region where most of the energy is, it disrupts this energy, and then all hell breaks loose. So it starts disrupting the scalar toroidal environment, with almost all of the scalar field being absorbed by the black hole. So these very hairy black holes are dynamically unstable. However, the resulting black hole that you get, which is an approximately Kerr black hole, is again transient because it's again unstable against superradius. And therefore, it will grow hair again, albeit in a smaller amount. So in this sense, this is actually migration. So as a brief summary on the dynamics of black holes with sync hair in this simplest model that we are discussing here. On the one hand, near the Kerr limit, one may state that Kerr is unstable against superradiance, forming hairy black holes as transient states. Hairy black holes formed from superradiance likely to have only up to about 10% of the energy in the hair. They could be sufficiently long-lived to be astrophysical players, and this is especially interesting for supermassive black holes. Superradiance efficiency selects a scale which connects to this issue of the universality of the Kerr hypothesis. So if for all scales, black holes are well approximated and similarly well approximated by the Kerr metric. On the other hand, near the boson star limit, we could say the following. So the spinning boson stars are afflicted by a non-axisymmetric instability. And hairy black holes, where the scalar environment is gravitationally dominated, are in an unstable equilibrium. So the development leads to a migration to an approximately Kerr black hole. But then we go back there. Now, an interesting question is about the impact of self-interactions. So especially near the boson star limit. And in fact, it's known that self-interactions may mitigate or actually fully quench this non-axisymmetric instability of spinning boson stars. They also make them less toroidal. However, just from a geodesic approximation, one can see the origin is never a stable equilibrium point. So this is indicating that the mechanical instability we are seeing will remain for the very hairy black holes, even with self-interaction. But things could be more interesting in the Proca model, which is the one here. So, firstly, Proca stars are spheroidal, the spinning Proca stars, rather than toroidal. Moreover, this non-axisymmetric instability of the scalar model has not been seen here. It is then interesting to consider how black holes with sync Proca behave near the star limit. And then, just again, you don't see it here. From the geodesic approximation, one can see that the origin can be a stable equilibrium point for the spinning Proca stars. So that seems promising. So the story might be different for very hairy black holes with Proca. So Jordan, a lot of work ahead of us, huh? So from the viewpoint of GR solutions, I would like to comment that the sync is a very generic mechanism to endow spinning black holes with hair. So I've already mentioned one can add self interactions or replace the scalar by Proca hair. One can also consider other space-time dimensions and asymptotics. In fact, the first example of this sort of sync mechanism was in ADS5 by Diaz et al. One can add electric and magnetic charges. One can use non-minimal couplings and non-canonical kinetic terms. Construct different types of excited states. Using such excited states, one can actually build a scalar dipole and put two spinning black holes in equilibrium in an asymptotically flat spacetime without conical singularities. And moreover, there's also a purely charged version of all this story in which one can add this type of hair to rise the Nordstrom black holes, but it has its own twists, and that's related to your work. Um, so there's many phenomenological and theoretical aspects that have been considered for these and other models. For instance, there are regions in parameter space where some of these black holes have more than the one mandatory light ring. And but of course, the topological charge is in accordance to the theorem before. And it was a little bit in the observations of these specific examples that the idea germinated for this sort of topological charge and this sort of invariant in the black hole landscape that I was talking about. So let me end with some final comments and outlook. Now, one can make statements fully independent of the equations of motion about the geometric properties of black holes, like the existence of light rings. This is quite desirable, I would say, and it would be nice if one could do it for other things as well. Because, there's sort of things that might not be model dependent, but they are not obvious. And they could give us a kind of some sort of control on some general properties that we should expect from black holes. And of course, then the details will determine phenomenological properties and contact with observation. But that's a different story. Black holes in GR and beyond can have Haro bosonic fields with no Gauss law associated, and this sync provides a generic mechanism to endow spinning black holes with bosonic hair. In the family of models detailed here, the hairy black holes, they coexist with Kerr, or the appropriate generalization. They don't replace them, so they don't solve the singularity problem, or, they could perhaps that's something interesting, relate to the dark matter problem. So as ultralight scalars and candidates for fuzzy dark matter. And that's something that many people are interested. I think it's an interesting connection. So the dynamics of the black holes, and I've reported here some new results, is complex. That's an ongoing effort. Likely no solution in these models is absolutely classically stable against small perturbations, not even Kerr, only Schwarzschild. But timescales are important in physics, and this is what we should have in mind, especially if we are considering possible astrophysical roles. then theoretically, phenomenologically, the space of solutions is quite diverse. But there's some sharp non-curve features that can be present, multiple light rings, exotic fundamental photon orbits, multiple ergo regions, disconnected regions with stable time-like circular orbits. And these things have interesting connections to non-curve phenomenology, unusual images, backwards chirp in gravitational waves, unusual X-ray spectra, and there's some disk models, then there's astrophysical modeling that has to come into the game. Perhaps the most exotic features are in quickly unstable solution, but there's an interesting question of scalar versus Proca that I try to emphasize. Now, I do think that these families of solutions provide a rich arena for theoretical black hole research in fairly simple models, where, for instance, the initial value problem is well defined, which is something not guaranteed in many other contexts. Unfortunately, the numerical solutions of the numerical nature of these solutions restricts the wider use by the community to some extent, and ways around that would be very welcome. And there are some efforts in that direction. So, as an epilogue, I would like to share with you the following discussion. So, this is from the same book. So Jim was traveling through Omaha, Nebraska with Warren Buffett at the end of 2003. And the global economy at the time was bad. This was after these dot-com crashes and so on. One could see closed shops and bankrupt companies. And Jim said to Warren, everything is bad. How can the economy recover from such a thing? Jim, and this was Warren Buffett, do you know what was the top selling candy bar in 1962? Nope. Snickers, said Warren. And do you know what's the top selling candy bar today? Nope. Snickers. So silence followed. So the epilogue is that some things are the same as ever or change very little. And to find them is kind of reassuring. And there are black hole properties putting in our context that are sort of independent of model, like the case of light rings. Exceptions exist, but maybe they are mere curiosities, or in some cases, in the exceptions, one can find also an interesting pattern, familiar pattern, same as ever, like zinc, which is throughout nature. And a whole new family of possibilities opens up. And this is the example of these black holes with zinc bosonic hair. So with that, I'll and thank you very much for your attention. Thank you. Thank you.
So thanks,
Thanks,
Carlos,
Carlos,
for the
for the
very
very
nice
nice
talk.
talk.
Crispino
Crispino
left
had left
early,
early,
so
so
I'm the
I'm the
new
new
chair
chair
of
of
the
the
session.
session.
So
So
any
any
questions?
questions?
So
So
I
I
will
will
ask
ask
you
you
to
to
come
come
here
here
to
to
use the
use the
mic
mic
as
as
well.
well.
Are you recording?
So
Please.
thank you,
Thank you,
Professor
Professor
Herdeiro,
Herdeiro,
for
for
very
very
interesting
interesting
and
and
inspiring
inspiring
talk,
talk,
as
as
always.
always.
I have one curiosity, and the other one is more of a technical question. So I will start with the technical question. So when you have uh, the scalar field equation without the nonlinear interaction, the self interactions, you can do the Teukolsky equation and show that argument that you have different types of states, right? When you include the nonlinear interactions, can you do the same? Because you have like powers of the field, and the decomposition can get like powers. How do you show the argument in this case?
Um, you could do decoupling, meaning you could have that the scalar field is not small. I'm assuming the scalar field is small, so self interactions are going to be relevant, even if they have, right? So for phi small, the self interaction. Another thing is, I'm assuming that although the field is not small, it's not back reacting. So that you can do. Of course, in this case, then you don't have that solution. Well, I mean, there's ways to do this, and people have looked at non-self gravitating, so decouple scalar field with self interactions. But in general, for self interactions, you do not have a nice form, even if the radial equation you have to solve numerically. Um, it's a fairly simple equation, but if you include self interactions, you get a more complicated equation. But for instance, the group in Mexico, Juan Carlos, they have done this kind of thing. So to consider, an equation with self interactions on Schwarzschild, not on Kerr. I believe you haven't done this on Kerr, but on Schwarzschild, and they've solved this as a non-back reacting problem. And I think that you've tried as well to do back reaction. So there's several groups that have tried to do this. You call it a decoupling limit in that case. Because if the field is small, then the self interactions are irrelevant anyway, even if the theory has self interactions. You see what I'm saying? Right.
The other question is about the type of the field, because you have shown, for instance, scalar field and Proca field, all of them are bosonic fields. And can you do this sync technique for computing black holes with fermionic here, for instance?
Yeah, fermions don't have this super radiance, right? So people, you can do Dirac stars, first of all. Uh, the issue of hair is more delicate. There is hair with fermions. Actually, there is some ways of doing it, but it's unrelated to this. With sync hair, um, this has not been achieved. You could think that this is related to Paredes, but it's something a bit different, perhaps. But let me tell you one thing. In that case, there's also a discussion about if that makes sense. Because the action for a fermion is of the order of h bar always. So, does it actually make sense to consider a classical black hole with this fermionic hair on top? Is it classical? So I'll leave you with the question.
Thank you again.
So, any other questions? I think we have time for maybe two questions. So,
Can I talk from here? Let me just I don't like to get out there. So thank you for the very nice talk. So about the first part, I think the first part of the lecture was about light rings and black holes. And you mentioned that you don't have to use the field equation, but somehow it's there, right? Because you have to assume that you will find a black hole solution. So it's a part of your background. No?
I don't have to assume it's a solution. I have to assume there is a black hole. Yeah, yeah. Now, black hole is a boundary condition. That's the point I wanted to emphasize. So, yeah, I don't assume any field equations. I would insist on that.
But my question was more directed to the light ring part. So I found it very interesting to this part in which you always have light rings in black holes. And at some point you mentioned about the relationship between light rings and the ring down. But this is not always very clear, right? Because
You know more about that than me.
yeah,
But
because I was actually wondering about whether you could have a black hole that always have light rings, but in some regimes it wouldn't have any natural frequency of oscillations or wherever. Because the potentials that you have, so I went on looking into the paper, the potentials that you have is a bit different from what one would expect for a black hole, right? So do you guys search for oscillation profiles or to see if they would have these natural oscillations, how different they would be from the light ring modes?
my impression is that if you have standard light rings, which are the saddle points of the potential, it should have a sort of standard ring down as well. Yeah. So, as you know, I mean, the association there, heuristic, is that the real part of the frequency is associated, to the orbital frequency, and the Lyapunov exponent is telling you about the decay, and therefore the imaginary part. And that makes sense because they are still unstable. And here I'm assuming, though, one thing which is not granted is that there is an instability. So it's a saddle point of the potential with stable in the theta direction and unstable in the radial direction, which is the standard case. I cannot exclude something very, very odd, certainly if it's not asymptotically flat, where you could invert these things. And that would keep the topological charge, you see? But you have more possibilities and more intricate ones. So imagine now that you have a black hole that you don't have, you have still a topological charge. It's asymptotically flat. You have topological charge -1, but you have 3 light rings. You have 2 that are standard and 1 that's exotic. So there's now a complicated potential and there's a complicated interplay. Now there's, there is a 2 light rings that would obey the standard, idea related with the ring down. So how do these 2 frequencies play, in that game? And the Lyapunov exponents. And when you perturb, there's the ring down of both. So there's a complicated thing. Now, in those spacetimes, you also need to have the stable light rings. So if this conjecture is about that the stable light rings induce a spacetime instability, then the spacetime would be unstable anyway. So I think there's a lot of interesting space for academic explorations here in that respect.
And in the end, maybe we find the same as that.
Very good, very good. You got my talk. So. Very good.
So one final question. We have time for one. Well, so if not, let's thank Carlos again.